Okay, hello everyone. Let's continue. And we are going to resume from the place where we left off. If you remember, during our earlier session, I couldn't show you an attack on a PLC. And that's why I put everything on the slides. I did screenshots, and I think that now you should be able to see everything much better, actually, because before that, during the earlier demonstration, the screen was not displayed very well in the broadcast. So once again, we're going back to our network. We find our SCADA system and the OPC server. We managed to find it with our special piece of software, and after we've connected to it, we need to add a group. And this group is nothing but a group of variables. We need it because in the OPC we cannot operate, well, not always, at least, we can't operate each variable individually. First, we must add them to a group, we must create a group, and after that, we'll be able to manipulate those variables. And this is how you do it. You add a group, and then we will see a pop-up window where we can review all of the variables, or as they are also known, tags. These are the tags on our server. You can see that in this OPC Explorer, in this client, we can list all the variables that we have already seen at the previous steps. So now we need to add variables or tags to a list, to our group, and after that, we'll be able to manage them. We'll be able to view the values and the qualities and the timestamps, when was the last time when this variable was engaged. And the interesting bit is that using write values, we'll be able to write them, which is the main attack vector onto the OPC server. What if the OPC server sorry, we lost sound for a second. In this case, you need not just the metric on OPC Explorer, because our OPC Explorer requires the name of the server. So in order to find the name of the server, you will have to start a different piece of software. I'm choosing this one, the OPCDA client. Again, you start this program, you connect to the server, find the name, and use it in the first client. The DOPCDA client, unfortunately, I couldn't make it work properly with the OPC server that has a multi-protocol master OPC. And that is everything that I wanted actually to tell you about the OPC. But now let's get to another topic. The topic of this session, the PLC, the most business critical component of the production facility, is this little box that controls absolutely everything in the facility. And we'll start with the internals of the PLC. Sergei Fedonin, a colleague of mine, helped me prepare this part of the presentation. Sergei is a real expert on reversing PLC firmware, and he is a real pro of reverse engineering. So once again, a PLC. As I have already mentioned, It is collecting inputs from the sensors. What kind of inputs? Well, it can be all kinds of sensors, like a pressure sensor or a temperature sensor. There are inputs. After that, the PLC applies a logic, does computing, and its useful work, its utility is in calculating outputs. A PLC can produce a lot of outputs. For instance, if we take a pneumatic valve or a fan or a motor, all these external devices are receiving outputs from the PLC. And the PLC is programmed using special software. There are development media as well, and they support different programming languages, including the IC-approved programming languages. You might have noticed that the PLC is somewhat similar to a PC. A PLC has memory, it has a RAM, it has inputs and outputs, it has code that controls it. So what's the difference? Actually, there is a difference. A PLC is intended for operation in a production environment, and this creates certain requirements and restrictions. An industrial environment is much more demanding. A PLC should be able to operate in a wide range of temperatures. It must be resistant to vibrations and shocks. It should be resistant to various aggressive milieu. Sometimes it is even coated or somehow protected from those hazardous conditions. Often, a PLC doesn't have a display. It doesn't have a keyboard. A PLC is usually installed in special cabinets. In terms of human interaction with PLCs, usually that interaction is remote, not physical. In order to control a PC, to program it, people use special operator panels like HMA and operator workstations. And everything that is connected to a PLC is connected via special input-output modules. Now, let's consider two main PLC types: the modular PLC and the compact PLC. They are also known as monoblocks. A modular PLC, as the name suggests, consists of modules. Usually the main module is called the CPU, the Central Processing Unit module. This is the brain, that's the main part that drives everything else. All other modules are hooked onto a rail, or how shall I call it, a bus, an input plane. This is the place to which they are attached physically, and also there is a special bus that they use to share data and to exchange data with the CPU module. You can take a look at our booth. We have a modular PLC. This is the CPU. It only has one switch that is either up or down. It can stop the program, or it can start the program on the PLC. There is also the memory card to extend inbuilt memory. Then we also have the communications module. Inside, we have an Ethernet module. In modern PLCs, you will find an inbuilt network component inside the CPU module. Over here, we have power. This is where PLCs are powered, and also we have two input-output modules. This is a digital I/O, and sometimes you also get an analog I/O. In our case, both of them are digital. You can see that this is the input-output. I'm sorry, the input module. You can see here that temperature and the emergency button are connected to the input module, and these are the connections of the output module. And also, there are the so-called compact PLCs, or, as I said, they're also called monoblocks. This is where you find everything under the same hood, the CPU, the communications unit, the input and output, everything under the same cover. They are less expandable, but they too have their use. Now, we can take this example and look inside the PLC. What are the internals? There are several chips. Our processor is marked here as 1. That's the system chip, the SSC module. We also have here the expansion slot. Number 4 labels a separate processor. The firmware of this PLC is processed by the CPU, so all the firmware, all the updates, all the downloads of the programs, all of this is processed by the central processor, which is marked here as 1. But the program itself is processed by a special processor identified as 4. And this is quite an often case, a frequent case. We see that kind of separation of duties in practice. 5 is where the firmware is stored. It's a flash memory unit. 6 marks a RAM chip, random access memory, and 7 is the connect to the backplane, this bus that I have already mentioned. Let's look into the inner workings of a PLC. A PLC is controlled by the so-called real-time operating systems. This is not a complete list of those OSs. These operating systems usually provide limited functionality for developers compared to conventional systems, but they are used or rather, they are developed with due regard for the special features of a PLC. VxWorks, QNX, they are all real-time operating systems. And usually in those systems, apart from Windows CE or RT Linux, either they don't have a file system, or it is quite limited, or they have their own special file system, or they wouldn't have this separation of processes. Everything coexists on the kernel. There is only separation of tasks, not processes. And if there is some failure in a task, it's not processed. After some time, the whole device may experience a failure. All of this is running on a central processing unit, most often you would find a RISC architecture. And the more traditional ones, the Intel's x86, x64, ARMs are popular, but there are other options as well. And we will talk about that in more detail tomorrow. In this firmware, well, we understand that data needs to travel. It needs a network. And not all operating systems come with a pre-built network stack. Often, third-party network stacks are required, and this is one other a backdoor for reverse engineering if you can find a network stack. And then you know what the firmware is, and you know about the known vulnerabilities in those stacks, and you can use those as well. So we have been saying that in the PLC, some kind of program is running. So how does it function? This program, in the beginning of the cycle, does internal checks. After that, it does the so-called input scan. The state of inputs is recorded in the PLC memory cells. After that, the program logic is executed, and it is the program that engineers or integrators coded. And after this program is executed, the output values are updated. And this happens every time, because this is a cyclical program. The program is usually written with programming languages, standard programming languages, and yes, they do not look alike, although the outputs, the results, are the same. You can program the same effect, the same output using different languages. Usually, a PLC vendor has a preferred language and a preferred development environment, and the PLC programmer chooses the language that, from her point of view, fits the purpose best. Let me say that those languages are structured in a way so as to satisfy any demand. LD, ladder diagram, it looks like an electric schematic, and maybe an engineer who is already familiar with those schematic documents would find this language easier to program on. Or ST looks like a high-level language, and IL it looks like an assembly language. And sometimes you can be more precise with an IL. The program executed by the PLC is executed inside the runtime. It is the environment where the program is executed. The inputs are read, And the same refers to outputs. Then we have the user program that makes use of the runtime system. You can use different functions of runtime. And in runtime, there are different counters and timers and the so-called markers. They are memory locations used for storing global variables. All of this can be provided by the runtime system. The PLC program, after the compilation, can be produced in two different ways. It can be compiled into bytecode, or it can be compiled into native code. Both of these cases are quite often. When the program is compiled into bytecode, like with Java, it can be executed on a particular processor. We have already seen a case with the Mitsubishi controller. Here I'm referring to a Siemens CPU. The native code, too, can be executed on a special device on a separate processor, or it can be executed in a special runtime, which is what Codesys does. Or it can be even executed on bare metal. That is also possible. Now, let's consider how PLC communicates with the outside, with the external environment. In its operating system, there are different capabilities. Usually, a PLC would support, let's call it, regular protocols like HTTP, FTP, SNMP, NTP. And for this, operating system services handlers are responsible. These services can be provided by the OS developers industrial protocols are processed by the so-called drivers of industrial protocols. In order to speed up processing of the information traveling on the industrial protocols, there are special processes. Well, sometimes there are processes that are, critical in terms of their responsiveness, in terms of time response. And sometimes there is an FPGA process, maybe, that only does processing or parsing of industrial protocol packets. And after that, this information can move on. So all these drivers and handlers, the runtime system communicates with them, it obtains all the information from them, and the runtime then runs the user program, as we have just discussed. And then also there are separate backplane protocol drivers. On the backplane, they really have their own protocols, several of them. Some of them come with an open specification, some of them are not documented. And an interesting data exchange also happens on the backplane. And now we are getting very close to finding out how we can get the firmware. I'm going to have a drink of water, and I'll give you time now to think about your questions. Very well. So how do we set about to get the firmware? I'm mindful of time. Probably will not be able to finish this topic today. It means that we'll continue with it tomorrow. Vladimir Nazarov helps me to get prepared for this part of the presentation. Sometimes in order to get firmware, you have to take special steps. And Vladimir is a specialist in those very special techniques. So, the firmware guide came out recently, and I'm sharing the link with you on the slide. It is a good guide because it is a summary of best practices of the experience of people who have immediate experience of this activity. And the illustration that you see now on the screen is what I borrowed from this guide, and it gives you a very good idea of all the different steps and stages that you have to go through in order to get the firmware, so that at an even later stage you'll be able to analyze it. Let's start with the most trivial option. That's downloading firmware from the website. You may think, so come on, now, what's to discuss there? Well, yeah, sure, sometimes it's enough to just download the firmware from the website, and you can analyze it immediately, but that's not always possible. Sometimes you would only download an encrypted firmware file. And then there are several options. You can Google. Maybe there are already known ways to decrypt the file. If that's not available, sometimes the hardware vendor, say, would be publishing unencrypted firmware, and only later the vendor decided to encrypt it. So if you manage to get hold of the old unencrypted firmware, it is highly probable that you will be able to find there the necessary functionality that will enable you to decrypt the current firmware version. But even that is not always possible, and sometimes all that we have is this encrypted firmware file. Well, then, nothing is left to do but to try to interpret this file somehow and to see whether it will be possible to decrypt it. It will be difficult, but it is still real. Sergei Fedonin, a colleague of mine, managed to do it on several occasions. So I know it's doable. There is another trick, which is also tricky, but again, you can do it if you have a completely encrypted firmware file. We'll see what this trick is a bit later, but now let's go back to the current slide. You may have an executable or an installation file with firmware on the website. You don't have the actual firmware file, you only have the installation file, and means that you will have to apply an extra effort to get hold of this firmware file out of the executable or an installation file. Another thing that sometimes happens is when firmware comes together with the engineering software capable of updating or flashing the PLC. And then the firmware can be found as part of this flashing engineering software. Moving on. The firmware can also be dumped from your device if you can't download it. If you already have SSH access, you can dump it using DD and netcat. Why netcat? Usually, well, if you have SSH, it means that the device is controlled by the Linux operating system. Also, if during download, primary or secondary loader is available to you somehow, if you can get closer to the device, if you can use a COM interface and get into the bootloader shell, or if the COM interface is somehow separated on the plane, then maybe you'll be able to get into its menu and use the memory dump commands, if they are there. Another thing that you could do is to find a debugging interface. Those interfaces, again, can be separated on the plane, on the chip, so that the developers could be debugging their own modules during development, or sometimes not everything is separated, just some pins, and that means that that you will have to find another way. One of the cases, let's consider a case from our practice. Here on the picture, you can see the PLC. And we have already seen one like this in the previous presentations. This PLC we decided to dissect it using JTAG. First, you have to find JTAG, you have to locate it. Thanks to the labels, it was easy to find the pins that were responsible for JTAG. You can see them now on the screen. And some other pins. Were de-wired and some were wired. We welded onto those pins. Vladimir Nasarov did it. The guy whose picture or whose name I have already mentioned here. Then we connected to JTAG, and then in its console we managed to connect to this debugging interface, and then using mem commands we read the memory. And this is everything that you need to know and to do to get access to the firmware. Another possibility, which will require some manual work as well, but probably It's less hard than the one that I have just shown you. That's dumping flash, getting firmware from the flash. Well, obviously, for this to be useful, firmware should be on the flash, but and not on the main memory slot. If this is the case, you'll be able to unsolder this flash memory, insert it into an adapter or a special reader. There are many possibilities there. There are many ways to read it. Of course, you have to be very careful so as not to damage the plate itself and the memory unit. There are different bodies as well. You can see here the so-called VGA frame or jacket, and its wiring and unwiring is very sophisticated. Let me share with you one other interesting technique. It is less invasive than unsoldering. It means, well, you can connect to flash RAM. When the device is off, the firmware is on main memory. When the device is off, when it's off, it's on main memory. When it's on, then we can read information about execution. The processor might decide to transfer this firmware into RAM, and we can make use of this feature. We can take a logical analyzer, and we can connect to the pins or to the wiring on the chip, and we can sniff the volume of data that passes through the device at the time of its switching off. And through this, we can get information about firmware. This is quite a working mode. You can use RAM and flash memory for it. However, well, actually, you don't have to use a very expensive logical analyzer to perform this trick. If everything else fails, is there another solution? Well, in fact, PLC vendors often include hidden functions into the device. One of them is reading and writing RAM over the network. If you manage to detect this function and use it, then you will be able again to read the firmware. Different vendors have different hidden functions. In case of Yokogawa, we found a special crash dump utility. Yokogawa engineers might want to have it to analyze failures of the controllers. A similar function exists in the development environment for Mitsubishi controllers, but this function is not always easy to find. And maybe, again, you will have to think hard about how best to approach this task. You'll have to rack your brains. And I'm done for today. Tomorrow we will continue with loading the firmware into the IDE. We'll discuss how we can analyze the firmware. Again, this may not be as obvious as you might think, because the firmware might exist in some unknown format, or it can be just an executable code. And tomorrow, starting from 4 p.m. Moscow time, we will learn how to deal with firmware analysis. Thank you very much for your attention. Thank you, Vyacheslav. Everything that you do is so interesting, and I'm sure that tomorrow more people will join this broadcast just for you. And we are done for today. We have listened to all the presentations. We've exhausted the agenda for today. Tomorrow, please be back at 1 p.m. Moscow time. Thank you very much, and see you tomorrow.
Спасибо, Слав, ты молодец.
Спасибо.
Thank you.